Hello, this is topic 10 of mlcourse.ai, and so we finally cover gradient boosting here. So you can see what we've covered so far, from exploratory data analysis through visual data analysis to machine learning to basic decision trees, then linear models, random forests, some unsupervised learning, and then finally gradient boosting. So actually it's a pretty important topic because most probably in your real-world application, gradient boosting will work the best. So we shall always be very careful with such exclamations because we know there is no perfect machine learning algorithm. So definitely if you deal with images, voice, or large collections of text, you'd better go to neural nets. So first trying some simple models. As we already discussed, there is some balance between linear models and decision tree-based models when feature dimensions are pretty high. So in our assignment 5, we compared logistic regression and random forest in 2 tasks. And we've seen that if the number of dimensions is really high, something like 100,000 or millions, then you'd better prefer linear models. But in real-world applications where you have some maybe from 200 features to some several thousands, and feature types are different, like numeric, categorical, binary, so most probably you'll go for gradient boosting. So typically I first check logistic regression and random forest, let's say in a classification task. And if I see that random forest performs better, then it's a nice signal that decision trees are going to work in this task. And so then I switch to gradient boosting, which is a bit faster both in terms of speed and memory as compared to random forest. And this I'll show in a practical part. Okay, let's first discuss basics of gradient boosting. So even first, just boosting. So in a nutshell, the idea is pretty much the same as in random forest in terms of that it's going to be a mixture of decision trees. So the final model is mathematically just the same, a composition of decision trees. So we'll illustrate the basic idea with add a boost. So it is known from some 1980s. And the basic idea will be building a composition in a bit different way. So remember in random forest, we trained all decision trees independently. So let's say if you have 100 machines, you can easily parallelize building 10,000 trees. Just each machine will be building 100 trees. And then finally, all trees in the composition voted. But here we'll do a bit better. We'll be building this composition iteratively, and this is best illustrated with the first well-known variant of boosting, ADA boost. So ADA stands for adaptive boosting. Let's take a look at a toy a toy classification problem. So we'll have 2 features and 2 classes, and we'll try to build some simple decision surface to separate red and blue dots. So why boosting is called boosting? Because it can actually take a very simple model and iteratively training such simple models, it can finally grow some non-linear, non-trivial decision surface. So it's a meta algorithm, so it will work with some base learner. And in our case, we'll take a very, very simple model as a base learner, just a decision tree of depth 1. So let's say at first iteration, we'll try to solve our task by building this decision tree of depth 1. So it's often called a decision stump. A very, very primitive thing to do. You see, we've got one feature, this feature 1, and we split it by a threshold. Let's say we trained it and it decided to assign everything to the left from this value as red and everything to the right as blue. So it will be the first iteration of our algorithm, and then we'll try to solve. So then next algorithm will try to make classification better. The crucial idea in AdaBoost is that our samples or observations will have different weights. So this is something new as compared to simple algorithms. However, even with logistic regression and random forest, we can specify sample weights. But AdaBoost changes these sample weights in a smart way. The idea is that we will be putting more weights on those instances that were misclassified. So in our case, we misclassified these three blue instances. And now we're going to increase their weight, and graphically we'll depict it as enlarging these blue dots. Okay, and so at the next iteration, it will be all the same, only that we'll treat these instances a bit more according to their weights. And by the same token, the weights of instances which were classified correctly now are a bit decreased, and so we hence see here smaller dots. Okay, let's say at the next iteration we build another decision tree of depth 1, and now it also thresholds feature number 1, but maybe at some another point, and now it classifies everything to the right from this boundary as blue, and everything to the left as red. So now we misclassify this bunch of dots, and we increase their weights. These three blue dots are now classified correctly, and so we decrease their weight, and so on. And maybe at the third iteration, now the decision boundary is built by thresholding feature number 2. So now it's built horizontally. You see, maybe it's a reasonable thing to do because we've got a bunch of red instances with large weights here and a bunch of blue instances also with large weights on the top. Okay, and now we also built a decision function, so we predict red in this region below some threshold, and we predict blue for values of the second feature above this threshold. We can visualize it like that. So we've got three very simple algorithms built at 3 iterations, and now we're going to make a composition. So we can visualize it as building such decision functions, and each of the algorithm will go with some weights. So we've got alpha 1, alpha 2, alpha 3 for the weight of each algorithm at each iteration. So we'll elaborate how we actually set these weights. And so finally we've got some non-trivial, non-linear decision function which performs perfectly in this very simple task. So it's a toy dataset, a toy task, but the idea will be the same. We'll take some really simple algorithm, and iterating with this procedure, we'll finally get some non-linear decision boundary. So before we go to pseudocode with this algorithm, I'll perform just one more intuition. So it's not going to be really strict, but the idea with these weights, so enlarging hard instances, is a very reasonable thing to do. So suppose you need to pass an exam, and there are really lots and lots of topics in this exam, including, let's say, math, physics, literature, history of arts, and so on. So suppose you pass this exam, maybe it's really very hard and it takes some 6 hours, and you get the results and you see that you passed everything okay, except maybe for biology and chemistry. And now suppose you are given a second chance to pass this exam, so maybe you've got some 24 hours and you're going to study more. And of course, if the exam is just the same, you're going to study biology and chemistry. Those disciplines that you failed at the first attempt. So you see, it's a very reasonable idea that you put more attention to those instances that are hard for you. So this is basically the main idea of boosting. Now I would say that this scheme is designed as a meta-learning algorithm, meaning that the base learning algorithm can be almost the same. Can be almost anything. But in practice, it turned out that decision trees became, I would say, perfect base learner for this algorithm, because decision trees are very quick to build, and they can easily so for random forest it helped that decision trees can easily overfit some small data set. So for random forest it actually helped, and so actually decision trees have a very nice property that they can quickly build a very non-trivial, non-linear decision surface, and it actually helps. So now we'll go to pseudocode of add a boost algorithm. So it's not really very easy to read pseudocode, but in this case I'll elaborate a bit more. So it's going to be not that hard. Okay, so we'll have sample weights. So sample or instance, in this context it's the same. So we'll put a weight on every instance, and it's going to be 1 over L, where L is the number of all our instances. So actually the length of our training set. So now we'll have some T capital iterations. So we'll build that many trees. For each iteration, we'll train our base algorithm. We'll call it BT. So it's not obliged to be a decision tree. It actually can be anything. Well, then theoretically there are some requirements that it shall be at least better than random guessing. So in a binary classification task, we'll only require that this algorithm performs a bit better than tossing a coin. So let's denote by epsilon t the training error of this algorithm at current iteration. So just a training error, so measured on the training set. And so when they started analyzing boosting theoretically, they made this requirement that epsilon t shall be at least worse than 1/2. So if it's lower than 1/2, then it means that our algorithm BT is a bit better than random guessing. Then we'll calculate alpha t, this coefficient with which will put a weight on this algorithm in a final composition. So this alpha t delivers this intuition that if epsilon t is low, this weight will be high. So if our algorithm performs nice, so epsilon is something close to 0, then alpha t will be something really high, so closer to 1. And on the contrary, if epsilon t is bigger, so if at current iteration algorithm is not perfect, then its weight in final composition, this alpha t, will be lower. There are some theoretical reasons why this function epsilon t depending on alpha t depending on epsilon t looks like this. So I'm not going into this right now, but the intuition is that the lower the training error epsilon t, the higher is alpha t, this weight in the final composition. Now the crucial thing, how we update sample weights. So at iteration t, we'll update weights wt by multiplying on this component. So let's actually elaborate it. Maybe you remember from the fourth topic how we covered margins. So you see here BT is the response of our base algorithm for an instance x, y, and we multiply it by yi. So it's a training set, so we've got a label yi. So this we called margin. So this yi multiplied by the answer of our algorithm BT is going to be margin. So let's take a look at this. So we'll be updating our weights at iteration t. We'll be calculating sample weights through their values at iteration t minus 1, so the previous value, and then we multiply by e to the minus alpha t. It's the strength of current learner at this iteration t. And then we multiply, so for instance number I, we multiply it by yi, and the answer of our algorithm bt for this instance xy. And again, I'm going to stick to this designation that values of our target feature are going to be either -1 or +1. This will be more convenient. Okay, so this we called margin for an instance xy. Well, it actually depends also on the yi, so it's actually a function of a pair xy and yi. So this is margin. Okay, and remember this that if margin is positive, then we classify an instance correctly. So if margin is negative, then we do a mistake, a misclassification. So when margin is less than 0, it stands for misclassification, or simply error on an instance. And the value, so absolute value of margin, stands for our certainty in classification. So if margin is very high, then the algorithm is sort of certain in its decision. And if absolute value of margin is close to 0, then the algorithm is not sure about it. So you see, this alpha t is always greater than 0. It's the strength of our learner at iteration t. So alpha t is going to be something from 0 to 1. And so if we see misclassification, then our margin is going to be negative, and then a positive value is exponentiated, and so weights actually raise. So we increase weights for misclassified instances. And by the same token, if margin is positive, then we classify an instance correctly, and then this instance weight is going to be lowered. And you see it's proportional to this strength alpha t. So alpha t is, as we've seen, is a function of epsilon t of current error. We'll informally call it strength of our learner at iteration t. And you see, it actually influences weights also very much. So we believe that strong learners actually influence weights more. And if a current learner is not very good, then it's not going to influence weights very much. So this is the basic idea, and you see, maybe you recognize here this intuition with chemistry and biology again, with passing these exams. So we increase weights of hard instances. Okay, so I think this step is crucial. And then lastly, we'll normalize sample weights after each iteration. So we'll just make them sum up to 1. So we calculate the sum of all these weights and then divide by it, so that all weights actually sum up to 1, and these weights will resemble probability distribution. And so then finally we'll return this composition of all BTs, of all base learners, multiplied by their weights alpha t. Let's go back to this margin, and remember we discussed that we can't actually minimize the number of errors directly, but instead we propose some loss function. So again, this indicator that margin is less than 0, it's going to indicate actually error, misclassification error for some, let's say I, for a pair xy, yi. And so if we build a simplest possible loss function, it's called 0, 1 loss. It's going to look like that. So we penalize our algorithm if it makes a mistake, and then we don't penalize it if classification is correct. Okay. So this blue will stand for 0, 1 loss. So as we discussed, we can't actually minimize it efficiently because you see its derivative is almost always 0, and here when margin is 0, derivative is infinite. Okay, so in case of logistic regression, we proposed logistic loss. Okay. So this is going to be log loss, and we derived its expression very thoroughly in topic 4. It was logarithm 1 plus e to the minus of margin m. And the idea is that it's some upper bound over this number of mistakes, and if we minimize log loss, then our number of mistakes, 0, 1 loss, hopefully it's also going to be minimized. So you see it's each time it's greater than 0, 1 loss. So if we minimize an upper bound, we hope that the number of mistakes is also minimized. Though it's not, strictly speaking, it's not obligatory. Okay, and if we do the same for AdaBoost, we can treat actually this as a loss function. Yep. So if we make an error, weights of such instance grow exponentially, and it turns out that it's going to be an exponent. So what we covered, how we changed weights of misclassified instances, this will correspond to this exponent loss function. So this is going to be AdaBoost loss. So it's something proportional to e to the minus margin. And so you see, actually, we can treat different loss functions standing for different algorithms. So let's go back to this picture. So we depict here the same. Here green is log loss, and actually after AdaBoost was introduced, it turned out that any procedure can be treated just as putting an upper bound for 0, 1 loss. So this phrase was not correct. I would say this picture generalizes different types of boosting that arise. And here orange line stands for AdaBoost. So you see it's an exponential function. But when AdaBoost was invented, then it turned out that it works pretty nice in practice. So first they didn't observe overfitting for AdaBoost. And then they started investigating why AdaBoost does not perform, does not overfit. So AdaBoost is known from some 1980s. And somewhere in 2001, 2002, the needed theory was developed, and it turned out that no, actually gradient boosting does overfit as any machine learning model. But it first worked really well in practice, and they started investigating different types of boosting. Because as you can think, AdaBoost has a really very serious drawback. If you think about it, if we have outliers, also misclassified, mislabeled instances, then AdaBoost is going to place exponentially large weight for such instances. So if we have outliers, then we'll misclassify them. Weights of these outliers will enlarge, then again we'll be misclassifying them. And so AdaBoost was very susceptible to outliers, and that's why they started investigating different types of different modifications. And so, for instance, this brown boost, as we can see, its loss function is depicted as this violet one. You see, it's a specific adaptation of AdaBoost to account for outliers. So you see it. When margin is negative, we do a misclassification, and then loss function increases. But at some point, brown boost would treat an instance as an outlier, and it started penalizing it less. So AdaBoost performed really well in practice. That's why it attracted a lot of attention and research. And at some point, they just realized that all these different types of boosting differ only in terms of this loss function. And so gradient boosting is a generalization of all such approaches, and it can actually minimize any loss function which is differentiable. Before we go to that, I will specify that these loss functions were designed specifically for classification, for regression, and even for ranking. And that's why even before invention of gradient boosting, they knew various algorithms for classification, regression, and ranking. And that's why gradient boosting as a generalization became a really very universal algorithm, suitable for all these three types of tasks, so most popular supervised learning tasks. Okay, so our topic number 10, this article is pretty long, so I encourage you to go through all the details. We'll cover only the basic idea of classic Friedman's GBM. So it was offered a bit later than AdaBoost, so AdaBoost was known already for quite a while. So Jerome Friedman offered in 1999, and so a couple of years later, this algorithm was theoretically analyzed. But this step is really very important. So this is the generalization of almost all known schemes to train gradient boosting. So the idea is very general. So as long as we have a differentiable loss function, this L is a function which takes y, our answers, and model prediction, which is denoted here as f. So as long as it's differentiable, we can apply this scheme, which will resemble gradient descent very much. So you see, either it's classification or regression or ranking. As long as you define a differentiable loss function, then you are okay, and you can create a gradient boosting training scheme for this loss function. So we'll have a data set, pairs xy and yi. We'll define a number of iterations. Here it's denoted as m. And we'll have a family of Bayes algorithms. Here they're denoted as h. So this will take x. And these Bayes algorithms are parameterized with theta. And so maybe we've got some additional hyperparameters here. So the main steps is that we'll initialize our first prediction just as constant. This constant will denote as f hat at step 0. So the best thing to initialize and make a constant prediction is actually to choose some gamma. It's going to be a vector of constant so a constant vector. The best guess will be just to minimize this loss function with respect to some constant vector gamma. And we'll take a look how it's done for mean squared error. So our first prediction at iteration 0 is going to be just constant, a vector of the same values for each instance. And then for each iteration, we'll do the following procedure. So we'll calculate what is originally called pseudo-residuals. So it's a vector which carries this information how bad our algorithm is performs at current step. So for that, we'll calculate gradient of our loss function with respect to answers f. So predictions or answers of our base learner are denoted as f, and we'll take a gradient with respect to these answers. So this will, if we take minus here, and if we calculate anti-gradient, so this is the direction where we need to go if we want to minimize the loss function. So you see it resembles gradient descent very, very much. So we calculate anti-gradient. So this is going to be the direction of the quickest decrease in values of this loss function L. But now we do it in this functional space. So our feature space will be all possible answers of our algorithm. So we are going to tune algorithm answers to minimize loss function. And now the most important step, we'll actually train our next base algorithm not with initial labels yi, but with these residuals r. So in some sense, we're going to provide a new training set for a new learner-based algorithm at iteration t. We'll just substitute labels yi with these pseudo-residuals. So the next algorithm will be trained specifically to minimize loss function. Yep. So almost the same idea as in AdaBoost, but maybe formulas are a bit complicated, but we'll go through a simple example with MSE. And so maybe you see it even from these formulas. So if R is an anti-gradient, so then we train our next algorithm to specifically minimize this loss function. And that's why we'll have this iterative nature of this algorithm. So at some step, let's say when t is 17, we'll have some errors. And at step 18, so next step, we'll train a decision tree specifically to minimize this loss, so this to improve these incorrect answers which were done by the model at step 17, the previous one. And then we can do a bit smarter again with this coefficient. Here it's denoted as rho at step t. So we'll add it to our composition so that again we minimize the loss function. So we have this f, the previous composition at step t minus 1. And now at step t, we are going to add our new predictions with some weight rho. And this rho will also be optimized via one-dimensional minimization. So we are going to minimize our loss function with respect to this weight rho. And so that's how we define rho at step t. And now we add these answers of our current model multiplied by this weight rho at step t. And then we update our current approximation. So now we, it's not perfect here. Yeah, this line means that from f hat, our current prediction, we go to f hat plus this new term that we defined for our new model predictions. And then final prediction is going to be this composition. So when we finished all m iterations, so then again our prediction will be the sum of all these terms. So again, model predictions with some weights. 1 minute. Okay, so let's go through a simple example to actually understand how it works. For a very simple loss function, squared error for regression. So actually, to explain how gradient boosting works, it's the most convenient to take regression, and our loss function will be just squared error. Okay, so to apply gradient boosting, we need to define this loss function, which takes y, vector of actually our target feature, and f will be model prediction. So in case of regression, we can set it to be squared error. Okay, so the most popular choice is mean squared error, but we can take just squared error. This coefficient 1 over the number of instances is not that important. And in our case, it's going to be just the sum of all these squared differences between yi and fi. Okay, so yi is the target for xy, and fy is prediction. Prediction for xy. And I iterates from 1 to L, the number of instances in our training set. Okay, this is a simple scalar form, but I will also write it in a matrix form, or matrix or vector, it depends. So it's actually the same as L2 distance between y and f. So it's actually, y minus f and L2 distance. So L2 distance is just defined with the same formula. I will show you how calculate these gradients, both in scalar way and in vector notation. So it's not very easy to calculate gradients with these metrics and vector notations, but if you elaborate, if you treat it as scalars, then it's going to be much simpler. Okay, now to apply gradient boosting, we need to know this gradient. So you see, as we defined it, here we need to know this gradient of L with respect to answers F. So for squared error, we need to define this partial derivative, which is actually denoted as Knobloch operator. So it's going to be gradient. Gradient of L is going to be its partial derivative, dl with respect to f. So this is the main point. This is gradient. Okay, what actually we see here, it's a partial derivative of a scalar. So our L is going to be just some number, scalar, and f is actually a vector. maybe I didn't stress it specifically, but both y and f are going to be vectors. So y is a vector of y first, and so on, yl for the last instance in our dataset. And the same for f. F is going to be f for x1, and so on, f for xl. So answers of our algorithm for all instances. And again, it's a vector. Okay, so how do we define a partial derivative of a scalar with respect to a vector? It's pretty simple. It's going to be a vector of the very same length as f. So if f is L long, then this partial derivative is going to be of the same size. And it's a vector of the very same length. And its first component will be dl with respect to df1, or is how it's actually f for answer for x1. Then the same for the second instance, the third, and so on, dl with respect to dfl. So actually, to find this gradient, we need to be able to calculate the derivative with respect to some f number j. So let's just take a look at fj, some jth component. So for component number j, we need to be able to calculate partial derivative of L with respect to fj. So in our case, our loss function is this squared error, so it's going to be equal to partial derivative of this whole expression with respect to fj. So here, e iterates from 1 to L, so this partial derivative will be really very, very simple. So if I is something different from j, then the corresponding derivative will be 0. So only one component in this big sum is going to provide a non-zero derivative when I equals j exactly. And this derivative is going to be so let's differentiate this yj minus fj squared. So it's going to be simple. It's 2 times fj minus yj. Okay. So this partial derivative is pretty simple, and now we can derive a formula for the gradient of the whole loss function. So, as we described it, this is going to be a vector of all these partial derivatives. So we'll have 2 times f1 minus y1 as a first component, and so on. For the last instance, we'll have 2 times f number L minus yL. And so these are all scalars, and now we can write it in a very nice vector form. So this gradient is going to be 2 times f minus y. And now, again, this f and y are again vectors. Well, we've got 2 here. That's the reason that sometimes they put 1/2 as a multiplier for squared error to make it 2 fade away. But, well, a multiplier is not that important. So you see, we started with a loss function. Our loss function was a function of y and f, and in a vector form it was L2 difference between y and f. And now we derive a formula for its gradient. So this is the original expression for L in a vector form. And now we derived an expression for our gradient, again, in a vector form. It's also a vector form. But you know, all this derivation was, in this case, it was simple. But the trick how you actually derive such formulas is very simple. You need to treat this expression in terms of scalars. So what we did, actually, we made all this derivation just treating this as actually in a scalar form. Yep. So we treated this scalar L as a sum of these scalar components, as we discussed. And then we calculated the gradient, first checking only one of its components. So this is the main trick how you derive such expressions. Yep, so you've got one choice, either to study this matrix and vector calculus and be able to differentiate these expressions in a vector form, which is somewhat involved. Alternatively, you can just treat your function, your scalar function, again as a function of some scalars, and then you treat this gradient. You take a look at this vector and take only one component, some gth component. And then its component is also going to be scalar, and you can define derivative as we did for a scalar, and then you generalize to write again a vector form. So this trick is very, very important for understanding neural nets. So if you're going to cover neural nets after this course, you'll see such tricks here and there. And actually, the main rule to understand neural nets is how you differentiate a complex function. And so, actually, the chain rule lays the basis for simple neural nets. And there you'll have a lot of metrics and vector calculus. And this simple trick to understand how it's done is also crucial to understanding backpropagation. Okay, now we know the derivative of our loss function with respect to answers, f. And we've got all components necessary to build gradient boosting. You see, these derivatives are actually very, very meaningful. So this gradient, what we actually got is, again, now just as bullets. So our loss function is standard error. Sorry. Okay, so we started with a loss function as just standard error, L2 distance. And we derived gradient of this loss function, 2 times f minus y. And you see, in our gradient boosting scheme, we are going to calculate these residuals, which are equal to anti-gradient. So if we put minus here, we'll have y minus f. And then we'll train the next algorithm with this target. So if we calculate minus this gradient, okay, I'll put 1/2 here, it doesn't matter a lot. So then the expression for minus 1/2 of this gradient is going to be just the difference between y and f. Well, you see, it's very, very meaningful. It's just current error. So it's the difference between our target and f. And so we see that at next iteration, we'll pass these as new targets, and our next algorithm will be will be trained to minimize this difference between correct answers and current prediction. It's very, very helpful to actually implement gradient boosting yourself. So if you keep track of our Kaggle dataset, Kaggle mlcourse.ai dataset, so at some point we'll share a demo assignment to implement gradient boosting yourself. Okay, we actually created this very, very nice assignment. We only going to share some of its version. So if you go here to kernels, here you'll be able to find all topics, all assignments. So if you maybe sort it by votes, so then just keep track of these demo assignments and you'll find demo assignment on implementing gradient boosting. We just don't share it right now. Okay, so if you watch a video, we'll share the link on YouTube just as a comment to this video. Okay, so basically this is the idea of gradient boosting. I really encourage you to try and implement it yourself for regression with this standard error. It's going to be really very, very simple. I'll only say, let's go back to this algorithm. I'll only comment all the necessary steps that we need for it. Okay, so for standard error, I will initialize our prediction with just mean target. Yep, so if you minimize squared error, if you choose a best constant to minimize squared error, you'll just get a vector of means. You can derive it yourself, this simple challenge, but just try to calculate this expression for standard error, for square difference between answers and some constant value, and minimize it with respect to this constant value, and you'll easily get that it's going to be equal to just mean or average value of your target. And then for some number of iterations, we'll calculate this gradient or anti-gradient as we've seen, just the difference between y and f. And then we'll pick up decision tree regressor. Yep, you see our target is actually a numeric vector. So now we train a decision tree regressor to predict this difference. In a simple case, you can just set rho equal to 1 and add it to your current prediction, or you can also implement this one-dimensional optimization to find nice weight for your new prediction, but it's obligatory. You can just set rho to be equal to 1 for simplicity. Okay, so go through this step-by-step example in our paper, how it actually works. Try to implement it yourself. It's going to be very interesting and useful actually to understand the basics of gradient boosting, the algorithm which works really very, very nice in practice. And so in the next part, we are going to take a look at how it works in practice, in particular light GBM implementation.